All right. Well, I want to respect all of your time, so I will get started. And yeah, I just want to welcome you all. Thank you so much for joining us this evening. My name is Shannon McManus, and I am the Director of Professional Learning here at the Museum of Science in Boston. I was a former high school physics teacher and now am happy to be working at the Museum of Science with our Youth Engineering Solutions curriculum. We are situated here in Boston, Massachusetts. So I know there's a couple people who are coming from all over, but we are at the Museum of Science in Boston, and the Youth Engineering Solutions is a curriculum that really stemmed from the Engineering as Elementary curriculum that started our research around the EIE and engineering curriculum started about 2 decades ago, and we've recently kind of rebranded ourselves as our Youth Engineering Solutions curriculum because it encompasses much more of what we do. We've kind of expanded beyond the elementary level for engineering and are now working at pre-K through middle school. And so we are now Youth Engineering Solutions. I'm hoping that today, by the end of this session, by the end of our time together, you will all become familiar with the engineering plastic filters unit. That is one of our Yes Elementary units. And also hoping we take some time to consider the opportunities that students have to engage in the practice of engineering. And really our goal is for students to kind of walk away from our STEM units developing a new identity and a way of thinking about themselves that they can engineer. So I see that some of you folks are here to learn more about the curriculum. And yeah, it's great to see. I see some folks that I know, some science teachers from my kids' schools. So thank you so much for being here tonight. Yeah, so I'm hoping that we can get a lot out of this webinar tonight. So just a general overview of the curriculum in general, all of our Youth Engineering Solutions curriculum, and specifically the plastic filters unit that I'm going to kind of dive into today, is that it's designed for an in-school setting. It consists of 9 45-minute lessons, which can be very adaptable. So what's so great about the units is that, if you're already teaching something about food chains and ecosystems, then you can integrate this unit in particular very easily into that content, and so you can kind of move those lessons around and work with them as you wish, as you are teaching other content. And it's designed as an upper elementary unit, really for grades 3 through 5. But the science content that connects to is ecosystems and pollution. And so we've done an alignment to the next generation science standards. And this plastic filters unit specifically aligns with the NGSS grade 5 science content. I'll actually put the link to the document that I'm sharing here in the chat. So you can take a look at that. All of our standard alignments are on our website, so you can look a little bit more in depth as to how we address some of that science content and how you'll see some of those standards play out in the unit itself. So I just wanted to kind of situate us, kind of what to expect when you first kind of open that teacher guide and take a look at the unit. And another sort of general approach, which is true for all of our units that you might find on our website, is this approach to engineering learning, this framework that we have. And I'll kind of break these pieces down. So you'll see these kind of 4 pieces: authentic engineering practices, asset-based pedagogies, socially engaged engineering, and all of that kind of points to, as I mentioned at the beginning, and our goals, are the shift in identity, how we want students to kind of think about themselves after they engage in an engineering unit. And so you'll see we've expanded upon, the next generation science standards has 8 science and engineering practices. We've expanded that after doing a lot of research, talking with engineers, thinking about what it really does mean to engineer. We've come up with these 16 engineering practices. And as we go through the unit today, so I'm sort of situating this framework for you all before we dive into our plastic filters unit. And as we go through lesson by lesson, I'll highlight different examples of how you might see some of these engineering practices play out in the unit, how we expect students to sort of engage in the activities themselves, and at the same time, use and display some of these practices and think like engineers and behave like engineers, which is what these 16 practices are designed to do. And so we've shaped our curriculum so that students are engaged in all of those practices as they go through the unit. Another kind of dimension of that framework that I shared is this idea of socially engaged engineering. And so again, I'll highlight as I go through the unit kind of where you might find these things in the unit itself. So, we always try and situate this engineering challenge in a societal context, one that kids can relate to. Students can maybe even know about this context and kind of experience it in their own lives. We also, as we get into the upper grades, really want students to think about the impacts of maybe their solutions on individuals or groups or systems. And so we encourage kids to think about who is most impacted by some of these problems that we're trying to solve. And then finally, we always want kids to think critically about the impact of their engineered solutions. Does it work for everybody? Does it not? Is it impacting anybody in a way that maybe we didn't expect? So that's one of the other ways we want kids to really think about their engineering design in a social context. We also, as we go through, you'll see some of the resources that we have really try and lend itself to this asset-based pedagogy to really try and leverage students' prior knowledge and experiences. When students come into our classrooms, they're bringing so much knowledge, they're bringing so many experiences, lived experiences, and we can tap into those. And we want them to help to make some of those connections in the classroom. So we try and bring some of those opportunities into the lessons. And we also, maybe they haven't been familiar or haven't explored some of the materials that they're going to engage with in the design challenge. We want to make sure that we provide opportunities for them to become familiar with materials and have some of these activities and lessons be very multimodal and flexible for them. And all of this is, again, as I mentioned, lends itself to shifting this idea of engineering identity in students. We actually intentionally use very low-cost materials in our kits because we want kids to go home and keep playing, keep engineering. I call it playing, but keep engineering because we are using popsicle sticks and we're, just kind of using everyday materials that they can think carefully about and critically about and how it might help their design. We also provide role models for them with diverse demographic characteristics so that they can understand that anyone can really be an engineer. And then we also really try and nurture their own identities. So we call them engineers, and we can refer to them as doing engineering so that they really can see themselves as engineers. So that's the general framework that we have for all of our curriculum. And I just wanted to highlight that before I start to dive into the curriculum itself. So today, I'm just going to use this one unit, our engineering plastic filters, the one that specifically, aligns with 5th grade NGSS science content on ecosystems, but also can be used really at any point in an upper elementary grade level. So this is our engineering plastic filters unit. And the first lesson, and this is actually the first lesson in all of our elementary units, is what is engineering? And all of our lessons have this guiding question: how do engineers solve problems? And to just start us off here, we can put our vocabulary word engineer onto our little virtual word wall here. And an engineer is a person who thoughtfully uses a process to design something to solve a problem. And so what we ask students to do after we introduce them to this word engineer is we show them this picture. what is the problem here? And oftentimes, there's a couple of problems, but oftentimes they identify pretty quickly that there's no bench at this bus stop, and that some of these people who are sitting at the bus stop really could use a seat. And so we say, yes, that is one of the problems of that bus stop and that scene that you're seeing. And so we asked them to create a model bench. So their task as engineers for this lesson 1 is to really just design a model bench and start to explore what it means to engineer. And we can add this word model to our word wall here as well. And so we've identified, we let our students know that your task is to be an engineer and design a model bench for people to sit on at a bus stop. And this is our criteria. What our bench needs to do is it needs to be 3 to 4 inches tall, 12 inches wide, and support at least one person's weight. Now, not a real person, but typically we use a little wooden block as our person. I have this little squeezy person here. You can bring in toys, little toy figurines to sit on the bench. So it doesn't have to be a real person at all, but something small like a dice or any kind of figurine that you want to sit on that bench. But some of their constraints that they have during their design is that they can only use 5 sheets of copy paper, 6 inches of tape, and they can use scissors and rulers as tools, but they cannot use that in their design. So they're given about 10 minutes to solve this challenge. But first, we actually allow them to explore the materials themselves. So I'm hoping this isn't too small of a screen for you to see, but we ask them to think a little bit about what you can do to the paper. What happens if you roll the paper, or if you fold the paper, or if you stack the paper? Let's just try and think a little bit about the different ways we can use paper to make a bench. So there is a little bit of an exploration in terms of like just thinking about the different ways you can use the paper in your bench. And then we also know that since this is our first time engineering together, because it's lesson 1, we may need some help working together. And so here are some sentence stems and some prompts we can use to help us work in teams, because students will design this bench together as a team. Typically in the upper grades, we think of groups of about 2 to 3. And so here are some sentence stems that might help them to collaborate. Like, I think we should maybe stack our paper because why? So we ask them to provide some reasoning behind why they want to do what they want to do, and some other, if you want to ask a question, what do you mean? Or I don't think that will work because, or that is a good idea because. So here are some sentence stems to really help them work together. So then they would go through, they would design their bench, and after that, they are introduced to an engineering chant. And really, this is kind of helps them to get in the engineering mood. You have just now, this has been their first experience. Now, sometimes people skip this lesson if they do multiple units because it is the same lesson. But it really is just this first opportunity for them to think about what engineers are and how they solve problems. And so we can ask them, did you use the ask step? Did you imagine? Did you make a plan? Did you create? And did you test? And if you did any one of those things, then you were engaging in the engineering design process. And so that's, kind of the goal of this first lesson, is to really get them thinking about this problem solving process that even without knowing it, they went through and they designed their bench and they likely did many of those things. And so they were engineering. And they can sing this chant to get excited about engineering. And so just as a quick reflection, when you think about this first lesson, and we kind of, just the way we specifically designed it was really as a way to practice some of these engineering practices. We want students to recognize that engineers use a structured problem-solving process. Now, they may troubleshoot a little bit throughout that process and test some things, but they're always kind of asking questions and imagining ideas. And this is a structured problem-solving process that they can use for engineering and for many different things. And also, it's a great practice for working effectively in teams, because for the rest of the unit, There is a lot of teamwork. And so we want students to get ready. To engineer means to work effectively in teams. And so this first lesson also provides some opportunities for them to practice that as well. And feel free, I meant to also say at the beginning, I am kind of monitoring the chat here. I'm happy to answer some questions as we go along in both the Q&A and the chat. But okay, so as we get into lesson 2, now the students understand what engineering is, and now we're going to introduce them to a larger problem that they're going to need to solve. So in this lesson, they read a comic that introduces them to the story of plastic pollution in Mobile Bay. Oh, great question. We are not missing the improved step. You'll notice in our engineering design process here, there is an improved step. It's not part of the cycle, but it basically just points this arrow around to say, okay, keep going. If you want to improve, you actually need to go through the whole process all over again. You need to reimagine, replan, recreate, retest. So the improve is part of the design process. It's just not a specific step that's kind of in the circle, but it's this arrow that kind of curves around there. Thank you for asking about that and for getting clarity on that. And so our comic book, and so this is kind of how we situate the problem for students here, is the problem with plastics. And this comic takes place in Mobile Bay. And our two characters here are going fishing with their dad, and they're noticing all this plastic in the bay. There's water bottles, plastic bags, food wrappers. And as they're fishing with their dad, they're pulling up their net, saying, okay, let's see what we got. And then their dad pulls out, oh no, it's just one fish and it's too small. And they're thinking it's probably because of the plastic. So they go to a community meeting and they see that other people in their community are recognizing the same problem. Some people in their community can't go swimming because the water is too polluted. There's some folks who are looking for wildlife. There's not many dolphins or pelicans. We have our fisherman who's, pulling up the nets and they're full of plastic. And then we also have another community member who's realizing that seafood is actually getting really expensive because there's just not that many healthy fish in the river. And so this is a problem that's impacting many people in their community. And so just to kind of bring us back to our word wall, this first little bit of a comic book has introduced us to some new vocabulary, plastic, and pollution. And so we can kind of tape those up to our word wall here so students can become familiar if they're not already with those two vocabulary words, because we're going to continue to use them as the unit goes on. And our guiding question for lesson 2 is, what is the problem in Mobile Bay and how does it affect different groups in the community? And so what students now do is they get these different cards, these different stakeholders in their community. They get all 7 of them. And what they're asked to do is to rank who is most harmed and who is least harmed by the pollution problem. And so their different community groups are grocery store owners, office workers, shoppers, swimmers, animals in the bay, boaters, and fishers. And they get these little cards and they just put them on their desk. And they put on the left-hand side, the stakeholders and the people in their community groups who are the least harmed. And then on the right side, they put the ones who are most harmed. Because when we go to design our solution to try and solve this problem, we really want to think about who is most harmed and who should we really design for. And then students also think a little bit about, have you seen plastic in your own community? And why do you think plastic pollution might be a problem in your community? So they actually do a little plastic pollutant scavenger hunt around their school. And they see how many pieces of plastic they find around their schoolyard, in their school. And yeah, I just want you to think a little bit about if you were to kind of take your students on a walk in your school or around your schoolyard, what might that look like? How many pieces of plastic might they find? What do you think this might look like in your context? And so, so that's lesson 2 is, again, having them think about who's most impacted and having them really tie this problem to their own community. So it really kind of taps into this idea, that socially engaged part of our framework for engineering learning. And so you'll also notice we have these when you start to look through our curricular resources, which are all free and available online, I can show you where they live at the end, letters to send home with parents so that they know what you're talking about and the problem with plastics, and so that they can start to either learn more about plastic pollution or different ways that they can talk about plastic pollution with their students and talk about this unit with their own kids. So again, I just want to highlight in the second lesson some of the ways that we this particular lesson ties into our framework for engineering learning. And primarily this lesson really situates itself in this socially engaged context. We're really trying to get students to think about this societal problem and that we need their help, and also for them to think about the impacts of the problem on different groups. And so you'll actually see I have a video of students who are actually doing that lesson, doing lesson 2, where they're talking about how it impacts different groups. So I'm going to press play. It's just about 30 seconds long. So we'll see an example of students having that discussion about who is most harmed when thinking about plastic pollution in the Bay.
I would say this would go all the way down here. We know this.
That's the most though.
Yeah, this is the very top.
And then it's
Fishers, because they depend on fish to get money. Office workers, they don't even interact with fish.
boaters, they don't.
Actually, yes, they do. Because if there's too much pollution in the water, the boat can't sail.
Okay, so you can see, I just wanted to make sure, I think everybody can hear okay, but you can see that they're really thinking about, the people in the office, they're not even impacted. They're not worried about plastic pollution, but boaters are, swimmers are, and fish definitely are. And so they really get to kind of connect and see how this problem impacts different groups. Which then takes us into lesson 3, because what they start to realize is actually, I think the group who is most impacted probably the organisms in the ocean. And so now we should think a little bit about those ocean ecosystems. And so in lesson 3, we're focused more on that group that's most harmed. And so we kind of come back to our characters and our comic book story, and they're, really realizing that plastic really doesn't seem to be good for the animals. It can get stuck inside them. They can swallow it. They also are remembering this curlew that they saw that had plastic stuck around its beak. So they're really just thinking about all the different ways that plastic could probably hurt organisms. But they're also curious because how does a fish get sick from a water bottle? And so they remembered a scientist that was at their community meeting, and they give her a call and they say, well, plastics, and the scientist is saying plastics really actually never go away. They just break into smaller and smaller pieces. And so students are starting to realize just through this comic book and be introduced to a couple more vocabulary words that in 35 to 60 years, those plastic bags are going to be tiny pieces floating in the bay, which are called microplastics. And so now they're thinking about how their bay also connects to the Gulf, and the plastic can really just also spread from their bay to other places in the ocean. And so they want to learn a little bit more about how plastic affects the ecosystem. And so our guiding question for this lesson is to think about what happens to plastic waste in the ocean and how does it affect living animals. And so students are given these plastic breakdown cards, and they are just asked to take a look at them and think, how long do you think these plastics have been in the ocean? So arrange those cards between the shortest amount of time and the longest amount of time. And they look at the pictures and they start to realize that, there are sort of these bigger plastics. They're large pieces of plastic, more than 25 millimeters long, that probably haven't been in the ocean for very long, haven't been in water very long, because they're still pretty big pieces. And we also have these mesoplastics, which are medium pieces that are 5 to 25 millimeters long, probably been in the ocean or in water systems for a little bit longer because they're more broken down. And then finally, these microplastics are very small, tiny pieces of plastics that are less than 5 millimeters long. And so all of these new words we can add to our word wall, because we're going to kind of continue to think about how these plastics impact organisms. And we want students to have those up on their wall so that they can kind of refer to that vocabulary. But now they think about different organisms that might be in the ocean. And so they each get kind of their own organism, and they think about how plastic might affect different animals in the ocean. So how do you think a Gulf stone crab might be impacted by the different sizes? You know, what's the microplastics going to hurt it, or the mesoplastic's going to hurt it, and the manta ray and the krill. So they think about the different organisms that are in this Mobile Bay food chain, and how plastics might affect it. And then, you know, they flip over those cards and they realize that manta rays can actually, these large fish can ingest tiny pieces of plastic that are in and around the plankton that they eat. So those people actually eat the plastic, or sorry, those organisms will actually eat the plastic. And then they start to think about, okay, well, how are these organisms situated in the food chain? So if one organism is impacted by plastic, how is that going to impact the rest of the organisms in their food chain? And so really just thinking about how plastic pollution is a problem in the larger ecosystem. And then finally, they've, you know, kind of really thought about the impact on ecosystems, of plastic pollution on ecosystems. And at the end of this lesson, we also ask students to help us make our model bays. And so you'll see all of these slides are also available to you online, so you can use these slides as you're teaching. And it really just, you know, these plastic bins come with a material kit if you purchase the material kits. And we give instructions, and we show kids this video of how to create their bay, because we actually end up drawing some lines. This is going to be their bay. Draw some lines on the bottom so that they can, that helps them to do their testing in the end. And so this video just shows kids, do this setup for you, how to set up their model bay. So we don't have to watch all of that, but you'll see they also end up attaching this piece of, it's a shame that our bay is made out of plastic, but that's just the material. We'll talk about that in the next lesson. Why is plastic used so much? Because the properties of plastic are very helpful in a lot of different scenarios. And so this little cup here represents the river that flows into the bay. And so this is another video. This is how we'll model plastic pollution. So I just wanted to share that with you at the end of that lesson. And so you'll notice as well in this lesson 3 that we're really trying to get students to think about the problem in a more of a societal context, you know, to really think critically about the impacts of the problem on different groups, which in this case are the ecosystem, the animals in the ecosystem. And let's just see some kids in a classroom having this conversation and thinking carefully about how this will impact organisms in the ecosystem.
30 seconds to a minute. Why is it important to solve this problem? Go ahead.
Well, if you don't solve it, fish are gonna die. Simple as that. Main idea. Fish are gonna die if you don't do it. Or fish animals, frogs, any aquatic animal that lives in water.
And it's gonna harm us too, cause we can't drink water if it's literally coming out, because water comes out of the ocean.
When people pollute the ocean, more fish die, and that means less food for the people that eat, like fish.
What could possibly happen?
When you go to the grocery store, the seafood prices might go higher.
Okay, what else?
And there's not going to be no fish, no nothing. There's not going to be like a live animal.
Who eats the fish? Other than people?
There's sharks.
Birds, other fish, right? So now they might not have food.
And then nobody's going to have food.
So then they would die off.
They might get diseases.
And we need food to be alive.
See what happens here? See how there's a series of events that can take place?
Yeah.
Okay.
So yeah, so students are really thinking about the impacts. If it impacts one organism, how is that going to move in the food chain and even cause problems for us when we, as we are part of the ecosystem and part of the food chain as well. And so again, when we think about not only this particular lesson really helps have students think about like the problem and how it's impacting different groups and organisms, but also we're asking them to apply science knowledge, their understanding of ecosystems, their understanding of food chains, and how that knowledge will help them solve this problem. And so in lesson 4, we think a little bit about, why do we use so much plastic? If it's such a problem, then let's just stop using plastic. And so Kayla and Antoine in this storybook are in this comic book are thinking the same thing. Well, let's just stop using plastic. Then the ocean animals would be healthy again. But as they're having this conversation, they're looking down at their lunchbox and thinking, oh, wow, well, how would we eat our lunch? Everything we have is wrapped in plastic. And then they also notice that, oh no, like a garbage can tipped over, how is it even getting into the waterways? It can get in a lot of different ways. Animals can move it, the wind can move it, the water can move it. And so they're realizing, yeah, we use a lot of plastic and it's getting into our ecosystem in a lot of different ways. And so the guiding question for this lesson is, how do macroplastic wastes get into the ocean? And so, they're thinking about how they use plastic, how it moves from place to place, and why it's so, if it's so harmful, why are we even using them? And so that question is really interesting, and we have students think about it. We use plastic in a lot of different situations. We use plastics to carry things in bags. We use plastics to wrap sandwiches. We use plastics in flower pots. We use plastics in squeezy bottles and our ketchup bottles. So why are people using technologies that are made out of plastics? And really, then we need to start thinking about the property of plastic. So let's say, for an example, an umbrella. So students have these sheets in their, this one actually isn't in there. Oh yeah, this is in their engineering notebook. If you were given an umbrella, think about an umbrella. What do you want an umbrella to do? What kind of properties do you need an umbrella to have in order to stay dry? Well, you probably want it to be waterproof. You probably want it to be lightweight because you don't want to carry around a super heavy umbrella. Maybe flexible, maybe you don't want it to rip or break. You probably want lots of these properties, but circle the 2 most important. And then you give them a little piece of plastic, a little sample size piece of plastic, and a little sample size piece of cloth. And think about, okay, if you want your umbrella to be waterproof, is plastic waterproof and is cloth waterproof? These are the most important properties for staying dry. If you want it to be lightweight, or to not rip or break, does plastic do that? Does cloth do that? And so which material is best for that task? And this is what engineers do all the time. They explore properties and uses of materials, which is why this lesson is actually really, really interesting and really important for students to think about why we use so many plastics, and it allows them to explore those properties and uses of materials. And so that lesson 4 is primarily just allowing us to really think about why do we use so many plastics and to explore those materials and why we use them for different tasks. And finally, in lesson 5, we start to think, we're still asking some questions and we're still in the ask phase of the design process, but we start to investigate the materials that they will have access to when they start designing. So they're introduced to the criteria and constraints of their design through this comic book. And so Antoine and Kayla, they're really thinking about, how can we solve this problem? We can't just stop using plastic because we know we kind of need plastic and we use plastic a lot. How can we solve this problem? They're thinking, oh, well, remember when our fishing net just scooped up all the plastic from the water? Maybe we could make a big filter. And so they bring that idea to the community meeting and they say, we've got some ideas. And the engineers and the people in the town are saying, oh, that's a great idea. But we need to better understand the needs of everybody. So our fisherman raises his hand and he says, well, I use the bay to go fishing. So it's really important that the plastic filter doesn't block any fish from moving into the bay, into and out of the bay, because fish need to move in and out. And the scientist agrees that, there definitely need to be room for fish to swim around or under the filter. We don't want fish getting caught in the filter. That would not solve our problems. Then there's a boater, and the filter needs to be far from the mouth of the river because I want to be able to ride around this filter. So if the pollution is coming out from the river, we want it to catch the plastic, but we don't want it to catch the boats who are coming out of the river into the bay, so people don't crash into that filter. And it needs to be removable. We want to be able to take that filter out every once in a while and clean it. And then we have the budget committee. It needs to not be too expensive. And so Kayla and Antoine are realizing, wow, there's a lot of complications for designing solutions to this problem. So they realize that, okay, there's some criteria. We want our filter to remove plastic and to fit in this zone. You know, we want boats to be able to move around it, and we also want it to be visible. But we have some constraints. It needs to be within a budget, and we can only use certain materials. And so we're going to add those words to our word wall. And also see, you know, we're thinking about all of these different users when looking at our criteria and our constraints. And so this is kind of our design challenge chart that we can kind of keep track of. We want to catch the plastic waste from a regular river. And also if the river's moving fast, if it's storming, we want to be able to catch the plastic. We want it to be visible above the water and fit within the filter zone. So, and also be able to remove it. So a couple of these criteria that are going to make it a little tricky for kids to solve. And so you saw how we designed the model bay. So again, this plastic bin is our big bay here. That's our model bay. You would fill that with water. And the smaller plastic cup that feeds into the bay is going to be our model river. And so what students are going to be asked to do is they are going to be asked to design a filter so that it catches the plastic pollution when it's flowing in from the river so that it doesn't enter the bay. And we now want to think a little bit about the properties of materials that are useful in our plastic filter design. And so we think about, okay, we have a lot of materials that we can use. Does it float or does it sink? Does it absorb or repel? So how do these behave? How do these materials behave in water? And so we have some new vocabulary words, repel and absorb, because we want to think about them when we're thinking about the different materials that they'll have when they finally go in and design. So you'll see, you know, now might be a time when you pass out the material glossary so that students can test each one of these materials to see how they behave in water. So when we dip this burlap into water, is it going to float or is it going to sink? Is it going to absorb water or repel water? Does it change shape? So we really just want to get a sense for how do these materials behave in water so that when we use it in our design, we'll know what to expect. And so they go through those tests. And this particular lesson really, again, allows them to explore properties of materials as well. But the primary one that we're focusing on for this lesson is this idea of criteria and constraints, because students are really introduced. This is why it's kind of an upper level. There's a lot of criteria that they need to meet. And they also have a budget. And so the idea that they need to balance those priorities is something that engineers do all the time and that we want students to think about as well. And so that's one of the primary practices that we focus on in this lesson. In addition to kind of exploring those materials. And you'll also notice, I just want to highlight here as well, you know, we have all these vocabulary cards, we have these material glossaries. We always want to provide students with the opportunity to explore the materials, develop a familiarity with the materials before we ask them to design, so that everybody has an opportunity to be successful. Not everybody's played with burlap before. Not everybody's explored what happens to a binder clip when you put it in a tub of water. We want to develop that familiarity so that when they come into the design challenge, they have some background content knowledge to apply to make a successful design. So you'll notice some of those aspects in that lesson as well. Not finally, I keep saying finally, it's not finally, but now we're imagining, I'm thinking we're finally going to design, which is often the fun part, although most of it is fun in my eyes. But the imagine and plan, where students start to think about, and we see Kayla and Antoine trying to think about what they need to do. How are we going to know when it works and how are we going to test it? And so they start to learn these new things. They have ideas and they brainstorm. And they start to imagine and plan their ideas. And our guiding question here is to think about how they can use what they learn to imagine and plan a plastic filter. And so here, this is all part of the engineering notebook where students start to realize, okay, there is a cost to these materials. So you'll see here our material cost. Your binder clip, that costs $400. Burlap is $800 per square inch. So that's actually a really great opportunity for some math connections as well. Craft foam is $500 per square inch. Your craft stick is $300. So you'll see these different prices that they need to think about when they're designing their filter. And so they'll get these scores for how expensive. So if your filter is pretty cheap from 0 to 1,000, then you get a high score. If you can remove your filter, you also get a high score. If you fit within the filter fits within the zone in the model bay, you also get a good score. If it's visible, you get a high score. And then when you finally test, you're going to count how many pieces of plastic. If you catch a lot of pieces of plastic, you're going to get a high score. So you want to try and get a high score here. And again, here's how you calculate your materials. And so they go through and, I mentioned before, they test two different ways, one with a regular flowing river. So you kind of pour that plastic into your bay in a sort of slow, you count to 3, 1, 2, 3, and you pour it through. But then you can also have a storm event. Oh no, sorry, that's the regular. This is the regular flow. And this is the storm event.
Okay.
Just kind of dump it event. And from here, and kids need to also identify together as a group, how are we going to count our pollutants? So oftentimes we have teachers who have used iPads to film the pouring of the plastic into the bay, and they wait 10 seconds to count. So basically, as a class, you can decide how you want to count. And basically this class has said, okay, it's been caught if plastics are in front of the filter. And so you just want to make sure everybody's ensuring that they're counting the plastics in the same way. And so once students have a sense for, okay, how we're going to test, how we're going to do all these things, now, how do you want to design your filter? And this step, this imagine step of our design process is a really important part for students to make sure that they have time to individually imagine, so that when they come together to make a plan with a group, they already have thought about it a little bit and they have something to bring to the group. So we always have them imagine individually. And then this last half of the lesson is for them to come together and come up with a whole plan as a team. So they need to collaborate a little bit. Okay, I thought of this one. I thought of this idea. How are we going to decide on our plan? And so they can share their ideas and say, okay, I think we should do this. I think we should use the burlap because of this, I think that that's a good idea because. So we also want to support them in this group work, because that transition from your own imagined idea to coming together and having to make a group plan can sometimes be difficult for kids to kind of give up or to compromise. And so it's all part of being an engineer. It's all part of working in a team. And we have these prompts here to help them through that. And you'll see in this particular lesson, we're really trying to highlight the idea that there's actually a lot of different solutions to the same problem. Most of the kids are going to think of a totally different idea. And so it's really interesting to see that engineers, there's multiple ways to solve problems, and and be able to envision those different ideas is a very important skill for engineers to have. And also this idea of working effectively in teams. So you can see here, this is just a sample student page of their sketch of how they thought about their design. They're going to use burlap and straws and twist ties to connect the straw to the washer. And you can see their thinking and imagining here. When we get to lesson 7, we're moving into our create and test step. And so we see Kayla and Antoine, they're testing. Oh no, but actually it's sinking. They're like, okay, that's okay. It still caught the plastic. And they're like, well, no, we need our filter to be seen by boaters and it's just not working. So they're realizing that they can improve. They can flip that failure. And so we want to have our students create and test their filter and see how well it performs. And again, now they also need to talk through the create phase, because once you get all those little hands going to get the materials, let's think of, wait, what was our plan again? We decided to do this. Well, what do we still need to do? What do we want to do? Because this can get to be a time when a lot of kids want to do similar jobs. So assigning roles is a nice opportunity here as well. And then I shared this as well, this storm surge. This is how you would test your filter. Put your filter in, because again, you want it to be removable as well. And then you'd scoop up some water, add your plastics, and then you'd pour that plastic pollution from the river. So it's flowing down the river. And now, again, depending upon how your group decides, you would count the number of plastics that stay in front of the filter. And then they would go through and calculate their score, and then they would reflect, did it work or didn't it work? How does it meet, does it work also the way you planned? And does it meet the needs of all the community members? And so in this particular lesson, we're again trying to work effectively in teams and really recognizing that they're constructing models, they're using prototypes, and they may also need to persist and learn through failure here. And so you can see students creating their filters here, and a student here who's pouring it in looks a little hopeful, and then looks a little disappointed maybe when the filter doesn't necessarily work the way they planned. Here are a couple example filter designs that kids have made. That plastic mesh seems to be a popular, although it is very expensive, solution. In lesson 8, we ask students to improve. And just like Kayla and Antoine, they realize we need to flip the failure. Our first try didn't work. And oftentimes our first tries don't work. And that happens with engineers all the time. And so this is probably the most important vocabulary word of all, is that you need to think about failure. It's something that does not work or is not successful, and that this happens to everyone. And that's why we have an improve step. And we want to look back at our test results to improve our plastic filter. And so, we ask students at the beginning of this lesson to look at your score. What worked well? Because something probably, you probably had a high score somewhere. What worked well? We should keep the designs the same because that worked well. But of the 5 scores, which one was giving you the most trouble? And maybe we can now improve that particular score. And we also want to think about, okay, so if that score was low, is that going to hurt the animals? Is that going to hurt the boaters or the fishermen? Or was it really expensive? Is that going to be a problem for the budget community? There's different groups you could redesign for. So even if your, plastic filter worked perfectly, maybe you could make it a little less expensive, or maybe you could think a little bit more about how are the boaters really going to get around, or how are the fish really going to make sure we don't have them get stuck in there. So there's always opportunities to kind of redesign. And so students go through and they flip the failure, they improve their design, and they go through the whole design process all over again and testing that design all over again with the same testing sheets. And, this is, again, one of the more important practices we try and have students think about when they engage in engineering, is this idea of persisting and learning from failure. And I do just want us to think about, how we normalize failure in our classroom, because oftentimes, in classes, students, there's either a right or a wrong answer, and they know that. But in engineering, there's an opportunity for students to learn from that failure. There's always opportunities to learn from failure and to improve their designs. And so we want to foster that skill and normalize this idea that sometimes you don't get it right the first time. Let's try again. And so I just want us to think a little bit about how we normalize failure and make sure students can persist and learn from that as well. And engineering is a great opportunity to practice that. In our last lesson, lesson 9, students reflect on the experience. They go to Kayla and Antoine, they're at the community meeting, and they're sharing their design. And some of the people from the community are saying, oh, well, if we use it, is plastic pollution not going to be a problem anymore? They're like, well, we don't think it's going to totally solve the problem, but it's going to make it a little bit better. And so they feel pretty proud of themselves that they've designed a prototype and thought about how they can improve the plastic pollution in their community. But they're also realizing, wow, this is a really big problem. Even if our filter doesn't stop all of the plastic, it's probably not going to stop all of the plastic, but it still could, those little bits can still go out into the ocean and hurt other animals that potentially live far away. And so they're thinking the work of an engineer is never over. And so then students do a little gallery walk of all the designs so that they can see how different people's designs are and what's in common, what are different, do any designs surprise you? And if you had more time to improve, what would you do? And then they think a little bit about the application. So let's say you removed one piece of plastic, because sometimes it's hard to remove all the plastic. Well, that means that it corresponds to 1,000 pounds of plastic waste. And so you could save one green sea turtle or 2 laughing gulls. If you got 10 pieces of plastic out of the river and collected it in your filter, that's the equivalent of 10,000 pounds of waste. And look at the organisms that you can save. So they start to see how their solution, how their model might have larger impacts on the ecosystem. So they look at this, and then they also see this map, and the bay that we're talking about here is Mobile Bay down in Alabama, which leads out to the Gulf of Mexico. But let's think about, where are we on this map, and how are the riverways in our area, where are they feeding into? So we also ask students to think a little bit about how this context might be situated in their own communities. And then the last step is where they think a little bit about themselves as engineers. And so at the beginning of this unit, did you think about who's affected by the problem that you're solving? And so if you consider others, how do you feel confident in considering others? Because that's what engineers do. They consider others. And so if you felt confident before and after in considering others, that's great. You can check both of those off. If you felt confident that you worked well with others before, or if you felt more confident after. So we really have them reflect on these engineering skills. Did you use your creativity? Did you learn from failure? Did you communicate well? And is there any one of these engineering skills that you want to improve? Because we want students to think about the skills that they used and how they can improve upon those skills, because that's one of the main goals, is definitely to learn about ecosystems and to do engineering design process, but to also think of themselves as being engineers who can continuously work through the engineering design process and improve their own engineering skills. And so that last lesson is really targeted on this idea of engineering identity. I just have one more classroom of students talking about their
Who can be an engineer?
Anyone.
Okay? And I hope that everybody realizes that, all right?
Yeah. Children.
Even children. So not just adults, but even children. Now, of course, if you're an engineer as an adult, guess what?
You know more.
Well, you will, but you also get paid because you can actually do it as a job. You can be an engineer as a career. You can go to college, learn more about the field, and then eventually you can spend every single day, for example, being a materials engineer, working with a bunch of materials, figuring out how they go together, making new materials from existing materials, okay? It is a wealth of opportunities for people who are interested in engineering.